Hello, I am Mohammad Shekarpur and I'd like to talk to you about noise suppression of hybrid silicon mode-electric laser using intracavity reflectors. Low noise operation of mode-electric laser can be achieved using high-quality factor lung cavities. In this structure, using an intracavity fabric period etalon, simultaneous optical frequency comb stabilization and supermode noise suppression were demonstrated for a 10 GHz repetition rate. In another structure, RF line widths of harmonically lung cavity silicon mode-electric laser by employing intracavity filter was reduced in 20 GHz repetition rate. So, harmonic mode-lacking of lung cavity laser is valid strategy for reducing a phase noise and timing jitter. We propose a modification of with intracavity configuration using intracavity reflectors (ICRs) instead of intracavity filter. Let's now turn to introduce proposed structure. Like previous harmonic mode-electric laser, the proposed structure has two gain sections separated by saturable absorber SA, directional couples light from the ring laser to bus waveguide, and low propagation loss silicon waveguide. The proposed structure consists of a combination of linear and ring configuration due to existence of ICRs. Because of implementing two intermediate reflectors positioned and both sides of saturable absorber symmetrically, this design is symmetrical. Thus, the pulse stream can be generated in clockwise and counterclockwise directions. In with intracavity configuration, as reported previously, in order to have pulses in both directions, two 50-50 multi-mode interference couplers should be implemented to establish symmetry. However, in the proposed structure, intracavity reflectors are inherently symmetric and their reflectivity can be optimized to further reduce the phase noise and timing jitter. Also, using ICRs, we can take advantage of colliding pulse effect to achieve harmonic mode-lacking. For numerical simulation of proposed structure, we extend the delay differential equation model to study harmonic mode-lacking of lung cavity laser. The first equation describes the slowly varying field amplitude, and the second and third equation describe the saturable gain and saturable loss respectively. Spontaneous emission is modeled in first equation by complex Gaussian white noise term with strength D. This term describes the amplification and losses of the electric field during round trip in the rim cavity. In delay differential equation, assume that the lasing is unidirectional, so that for modeling transient grating of colliding pulse effect, we define effective mirror model. Thus, as shown in this figure, for proposed structure, the delay differential equation is based on 3 delay time. The round trip time between ICR and center of transient grating determines the repetition frequency of harmonic mode-lacking. Turning our attention now to the effect of ICRs on dynamic results. In without spectral filter structure, all harmonic components H1 to H10 are generated with respect to fundamental frequency, that is 2 GHz. By increasing the unsaturated absorption JQ, which corresponds to reverse voltage, recovery time of the absorber decreases. On the other hand, rapid absorption recovery causes the unsaturated gain Jg required for the desired repetition frequency to rise. This behavior is in good agreement with harmonic regimes of repetition frequency as shown in this figure. However, harmonic mode-lacking regime of the proposed structure exhibits only H9. Also, significant increase in 20 GHz regime compared to the without intracavity reflector structure. Indeed, the symmetric ICRs can be considered as a Fabry-Perot cavity. This Fabry-Perot filter suppresses intermediate harmonics. We investigate this influence of the Fabry-Perot filter by applying discrete Fourier transform DFT to field power for without intracavity structure and proposed structure in 20 GHz regime. From the power spectrum, only 20 GHz harmonic component can be seen in proposed structure. But in another configuration, all harmonic components are appeared, causing amplitude distortion in time domain. Additionally, we investigate dynamic results of pulse widths and peak of pulses. In without intracavity reflector structure, by increasing unsaturated absorption JQ, the pulse width decreases and thus the peak of pulse strain is increased. Also, the mode-lacking operation tends to shift from higher harmonic to lower harmonic frequency. However, in proposed structure, the change of JQ do not lead to a significant effect on widths and peak of pulses. For dynamic of ring mode laser presented in previous sections, the spontaneous emission was not taken into account. By considering the spontaneous emission in modeling as a noise strength of D, the fluctuations in arrival times of pulses are appeared. These fluctuations can be quantified by the timing jitter. For calculating timing jitter, the repetition period of an ideal clock is obtained by firstly averaging over the number n of the pulse train and subsequently averaging over m noise realization. Timing spectral density is obtained according to the following equation. This term is timing fluctuation. For each realization J of noise, the timing fluctuation is defined by timing deviation of pulse train from an ideal clock with repetition period. In simulations, pulse train containing 30,000 pulses are used. The discrete Fourier transform DFT is applied to each realization of the timing fluctuations. Thus, by averaging over m noise realization, the timing spectral density is obtained. The phase noise spectrum is related to the timing spectral density. Finally, by integrating the phase noise spectrum over the frequency range, the RMS timing jitter is defined. The single sideband phase noise of tree structure are plotted in this figure. The use of selectivity filter in with intracavity and proposed structure leads to a reduction of phase noise by about 8 dB. In the figure below, by increasing the strength of spontaneous emission noise, the difference between phase noise of proposed structure and with intracavity structure demonstrated. As can be seen, the suppression of supermode noise in proposed structure can be better compared to with intracavity structure. The RMS timing jitter of proposed structure normalized to the RMS timing jitter of without intracavity reflector structure. As can be seen, the RMS timing jitter of proposed structure is decreased. Furthermore, the 20 GHz frequency repetition rate can be achieved at lower current, so the spontaneous emission noise decreases and further reduction of phase noise and RMS timing jitter can be achieved. Additionally, this figure illustrates a nearly periodic dependence of timing jitter on JQ and JG. To clarify the periodic dependence, variation of frequency repetition rate is shown in this figure. By considering this variation, we find that when TISI-H9 falls within the resonance regions, the stability of pulses is increased. In conclusion, the influence of the intracavity reflectors on dynamics, phase noise and timing jitter of ring mode-locked laser has been numerically investigated. By delay differential equation model, we can show the intracavity reflectors can suppress intermediate harmonics. We find a reduction of phase noise and timing jitter compared to the without intracavity reflector structure. Thank you very much